Hello, Honors Physics. The topic that we are looking at this week is called electromagnetic induction. There are two named laws involved with this. One of them is Faraday's Law, and the other is Lenz's Law. I'll be talking about both of those laws, doing a bunch of examples, mostly with Lenz's Law, because that one is more difficult conceptually. Faraday's Law is basically just a relatively simple equation, but Lenz's Law is conceptually tricky. Both of them are related to this idea of flux that I introduced last week. So as a brief recap here, you can think of flux as being a way of measuring the amount of magnetic field that passes through some given area. So like if I make a little loop, and there's a magnetic field in this space, those field lines go through the loop, and flux just measures that. How much field is there in that area? The formula for it technically involves a dot product of two vectors. So you need to know the magnetic field, you need to know the area in question, and then there's this cosine theta, because the orientation of the area relative to the field is going to be important. I have an area vector drawn here. Area vectors have to be perpendicular to their area. So in this case, where the area vector and the magnetic field are parallel, that'll be an angle of 0. And this is also the case where I'm like catching or intercepting the largest number of field lines. And cosine of this angle 0 is 1, so that represents a maximum value for the flux. If I begin rotating my area, I'm going to be catching fewer of the field lines, so the flux goes down. And if the angle is 90 degrees, then I'm not going to catch any field lines, because the field is sort of hitting the rectangle edge on, but it has no thickness because it's just an area, and so there's no interception there. Flux can also be negative if I were to continue rotating that rectangle so that the two vectors pointed in opposite directions. Then you'd get a negative value. Okay, so Faraday's Law is about the creation of electrical activity based on magnetic activity. We've already seen the reverse of that. We know that you can create a magnetic field just by having a current. You send electricity through a wire, it makes a magnetic field. Faraday's Law is about the opposite. You can also create an electrical current just by messing around with a magnet. And that's the basis for our entire electrical grid, basically. The way we get most of our electricity is by spinning a bunch of magnets around near wires. And that creates electricity in those wires, and that's how we power our entire civilization, basically. The way it works is that if you just have a magnet near a wire loop, near a coil, nothing interesting happens. But if you do something to change the amount of flux going through the wire loop or going through that coil, then you will get electricity. So again, if I just have like a wire and a magnet next to each other, nothing interesting. But as soon as I begin moving one of them around or spinning it, or if I change the size of the loop or something like that, that will create electricity. So the way I've stated it here is that any change in magnetic flux induces an electric field. Induce is just a fancy word for saying like makes or causes. So simply having a magnetic flux, not interesting. Changing the magnetic flux, that will create an electric field. And if you have an electric field inside a conductor, then that's going to make charges flow. It's going to make a current. So the way that we can most directly calculate this involves a quantity called EMF. You can think of this, for the purposes of honors physics, as being the same thing as a potential difference or a voltage. It's measured in volts, even. Potential difference, which is what you get like from a battery, if you make electricity with a battery. Potential difference is a special case of EMFs. It's like a subset of EMFs. EMF is a broader topic. But again, for honors physics, you can just think of it as being the same thing as a potential difference. And again, it's measured in volts. So that should feel pretty natural to you. EMF in olden times was an acronym for electromotive force, but we don't really use that term anymore, but we still use the abbreviation EMF. And when it comes to a coil of wire, the more times it spins around, the stronger the effect is going to be. If you've ever had the chance to like make an electromagnet out of a nail by wrapping a bunch of wire around a nail, you would have experienced this, that the more times you wrap the wire around, the stronger the effect gets. So that's Faraday's law. Just says if the flux changes, you're going to get an electric field. Lenz's law is about the direction of the electric field. And Lenz's law is very difficult to state in a way that is not awkward. I'm going to make a few different attempts, and I'm going to show you a bunch of examples. But Lenz's law is conceptually tricky. So what Lenz's law states is that when you get this induced EMF, like it could conceivably go one of two directions. If I have a little loop of wire, I can make the current go clockwise or counterclockwise. How do I know which one it's going to be? Well, that induced current, because it's a current, it also has a magnetic field. It makes a magnetic field. The magnetic field that's produced by the induced current will oppose whatever the original change in the flux was. So there's always an opposition or a resistance to change involved in any induction effect. And that opposition part is Lenz's law. It's going to take a while probably before that makes sense. That's why I'm going to do a bunch of examples. So just keep that idea of opposition in mind. This is the mathematical form of the two laws combined. This fancy E is the symbol for EMF. Again, you can think of that as like volts. The capital Phi is flux, which we defined before. The little t is for time. So it's the rate of change of the flux that determines how strong the EMF is. If you change the flux very slowly, the EMF is small. If you change the flux very rapidly, the EMF is strong. And then the capital N is just an integer for counting how many coils there are in your wire, like I was saying before. If you have just a single circle of wire, then it's 1. But if it wraps around 50 times, then it's 50. Okay, more about Lenz's law. I strongly recommend that you look at a bunch of the videos that I'm going to attach, a bunch of the other YouTube videos, because there's a lot of cool demos of this. But since I don't have any equipment here at my house, I can't show them to you myself. But there are some very weird and interesting demonstrations of this. So when induction occurs, that means that there was some kind of a change in the magnetic flux. And there had to be a cause for that of some sort. So something was moving around, or the field was getting stronger because somebody just turned on an electromagnet or something. Some kind of a cause for the change in flux. And the direction of the induced current will always be in opposition to whatever that cause was. It opposes the thing that caused it. So as an example, if you have a wire in some external magnetic field, and that magnetic field is getting weaker, the field that comes from the induced current is going to try to strengthen the field. And the opposite is true also. If you are turning off your electromagnet and weakening the magnetic field through a wire, you're going to get an induced current that tries to strengthen the field, to try to oppose the effect that caused the induction in the first place. Similarly, if there's motion involved, which is often the case, once you have an induced current flowing through your wire, that current is flowing through a magnetic field, because there has to be some external magnetic field already present for there to be a flux in the first place. So the induced current is going to experience a force from the external field, and that force also is in opposition to whatever was going on. So like in an electrical generator, there's a magnetic field that comes from either a permanent magnet or an electromagnet, and then there's a loop of wire, and it's rapidly spinning around inside the magnetic field. Lenz's law tells us that there's going to be a force exerted on that spinning wire to try to slow it down, basically. So it's almost like a kind of magnetic friction or resistance. That's how you know which way the current is going to go. It's going to be going in the way that causes resistance. So this resistance or opposition will always slow down whatever is going on. If you try to do a thing, induction occurs to try to stop you from doing that thing. But it's not going to completely stop you, it's just going to slow down the process. It'll spread it out over time. Here's a first example. I had this exact same diagram last week, when the only thing I was talking about was flux changes. So there's this magnetic field coming out of the screen. I have a square wire, and the magnetic field is getting weaker. So what that means is that the flux, the magnitude of the flux, is going down. It still points out of the screen, but getting closer to zero, it's weakening. So if the flux is weakening, I know that the induced magnetic field needs to try to bolster or reinforce it. So the induced magnetic field is going to have to look something like this. We've seen a bunch of wire loops already. So hopefully you remember that the magnetic field on the interior of the loop is going to go one direction, and on the exterior of the loop is going to go the opposite direction. We only care about the interior because it's the flux through the interior that we're tracking. And I am basically losing dots. Right? I had 16 dots in the first picture, but there were only 6 in the second picture. So the induction is going to make more dots. I've drawn dots in the x's here. Note that I haven't figured out the direction of the current yet. I'm only talking about the field. But I know from Lenz's law that the induced magnetic field needs to try to undo the change. So I've got to make dots. Now I need to think about the direction of the current. So if I imagine, I'm going to use the field production right-hand rule. I'm going to think about the right edge of the wire loop here. And I want to get my hand not taking up the whole bubble. So the current could either flow up or down on that edge. And if it's flowing up like this, then you can see that on the right side of my thumb, which is like the right side of the wire, the fingers are going into the screen. And that's what I want. I want X's on the outside and dots on the inside. So again, if I have my hand this way, the fingers are going into the screen on the right. They would be coming out of the screen on the left. I don't know if I can turn my hand that way. Really. So again, this is for the right edge of the loop. Fingers are coming out of the screen at you on the left. So that's the correct direction. On this side, the current needs to be going up. That means we go left here and then down and right. So that's a counterclockwise flow. That's the direction that the current can go to reinforce the weakening field. So I have many more examples of this. So this is the basic strategy. You need to first figure out what direction the flux is even going in the first place. Often that's going to be either in or out of the screen, but it could be like left, right, down, up, diagonal, something like that. But identify that initial direction. Determine whether the flux is going to be getting weaker or stronger. So think about the magnitude. Then you have to decide how you can oppose that change. Are you going to need more field lines going in the direction of the initial flux, or fewer field lines in that direction? So in the previous example, the way I was thinking about it, the way I said it, was like, oh, I need more dots. So if I need more dots, that could mean I would need more dots in either a case that I was losing dots, that's what we just saw, or if I were gaining X's, I would want to make dots to counteract those extra X's. Another example, if I have a magnetic field pointing to the right, but I'm losing flux in that direction, then I would need the induced field to go to the right. Similarly, if I had flux going to the left, but I was getting more of it, I would again want to make an induced field go to the right. My induced field is supposed to counteract whatever is happening. So if I'm getting extra stuff to the left, then I need to make some stuff that goes right. If I'm losing stuff that goes right, then I make extra stuff going right. Once you know what you need the field to do, then you can use the right-hand rule for field production to determine which way the current goes. So it's a multi-step process. Let's look at another example. This one, again, you've seen part of it before. This wire is being pushed into the magnetic field. That means that the flux through the loop is getting stronger. You can imagine as it enters the field, I'm going to get more and more dots. Right now there's 12, but in a moment, I'm going to be up to 16. So I'm getting more dots. To counteract extra dots, I should make X's. So the induced magnetic field will need to go like this. And if I want the magnetic field to go like that, I'm going to stick with the right edge of the loop again. This is what I did last time, but that gave me dots on the inside. If I flip my hand like this, now the fingers are coming out of the screen on the right. Wait a second. I can move my bubble. So my fingers are coming out of the screen on the right. That's the dot. And my fingers will be going into the screen on the left. That's the interior of the loop. And that's the X. So I need the current on this edge to be going down. That means it's a clockwise current this time. Next example. Again, you saw this one before. We're looking edge on at a loop which is being spun in the magnetic field. And again, this is the way a generator makes electricity. So as it spins, it's going to be picking up more and more of those field lines. So the flux goes up, and the flux is going to be increasing because I'm going to catch more of them. To counteract that, I should make field that goes the opposite direction. I need to make a flux or a field going down. So inside the loop, the field has to go down. I've drawn it kind of curved and on a diagonal because it's going to end up having that dipole shape. That's why I drew them curved. And it's going to be perpendicular to the loop. That's why I have it tilted. But you'll be fine if you just think it needs to go down. It's good enough. So to get a magnetic field going that direction, I again would use the right-hand rule. It's tricky to illustrate this since we're looking edge on, but the idea is that here where the wire is coming either directly in or out, that you are how do I put it? I'm going to hold up a switch game case for this. So this is just it's my Mario Kart 8 Deluxe box. So like along this edge here, the top edge, the current is coming out of the screen there. Then it goes down along this edge. Then on the bottom edge, it goes into the screen away from you. And on the back side, it would move back up again. So I've indicated three of those four directions. The top is coming out along this front edge. It goes on this diagonal, and then on the bottom, it goes back into the screen. And I didn't do the right-hand rule thing yet. So for the top part of the loop, my thumb would be like that. Drag the bubble over there again. My goal is to get a magnetic field that goes through the loop this direction. It needs to be going down through the loop. So on the top, if my thumb is pointing out, my fingers go down on the correct side. If I had my thumb this way, that would be making a magnetic field going the wrong direction on the inside of the loop. So the current's got to go this way up there. As you move down along it, my hand would be, how do I show this well? I guess like that. My fingers on the far side of my hand from you. That's the inside of the loop, and they need to be going down. Of course, it's all behind my hand. And then at the bottom edge, I need like this, so that my fingers look just like that magnetic field line I drew, and that's for a current going into your screen. Example 4. Again, I have this uniform magnetic field just chilling out, and my loop of wire is magically increasing the radius. So as the loop gets bigger and bigger, the flux is going to increase. I'm getting more and more X's. To counteract that, I need to make dots on the inside. If I make dots on the inside, I'm also going to make X's on the outside, but we don't care about the outside. To get dots on the inside, I'll put myself over here again. I need this direction, just like before. On the right side of the loop, if my thumb points up, then, no, I just lied to you. My fingers are coming out of the screen. I'm so confused. Hold on. And of course I'm doing this all actually with my left hand because of the screen around. No, this is correct. I want dots on the inside, and my fingers are You're seeing the tips of my fingers, so they're coming out of the screen towards me. So thumb up, that means that the direction of the current has got to be counterclockwise. And yay, I got it right. Example 5. I have this loop of wire and it is moving to the right through the field. You may remember this was a trick last week. The flux through this wire is not changing. And if the flux is not changing, that means there's no induced EMF, no induced current, no induction occurs. Even though there's motion, because this particular motion doesn't change the strength of the field or the area of the loop or their relative directions. As long as it slides along this direction, I'm not actually changing the flux. Example 6. All right, the first part here asks about the direction of the flux and whether it's increasing or decreasing. The bar magnet's magnetic field comes out of the North Pole, wraps around to the South Pole, and then continues straight through. But as long as we're in this space out here, the field from the North Pole is going to be going to the right. Something like that. It also spreads out or weakens as you get further away from the magnet. So if we drag the magnet away from the loop, the field is going to be getting weaker. So the flux is decreasing. Points to the right, but it's decreasing in strength. So this means that the induced field needs to oppose that. My field is weakening. I want to try to strengthen the field in response. So the induced field needs to point to the right. So let's think about the left and right sides of the loop is a little ambiguous. Depends on how you perceive the depth perception here going on. So let's think about the top. At the very top of the loop, I know I need to make a magnetic field that goes to the right. So I can either have the current coming out of the screen, but if I do that, the magnetic field on the inside of the loop goes left. But if I flip it around this way, how do I get my fingers most useful? That's not very clear. But if my thumb's coming out of the screen, then my fingers below the wire go to the right. So I want to put a dot for the current up here so that it's coming out. And then the current at the bottom has to be going in. Oh, I skipped a step. I said this with my mouth, but I didn't click it up. I need the induced magnetic field to go right to reinforce the weakening field. And that means that the current needs to be like this. Okay, we're almost at the end. I have a current going to the right. I have this loop of wire nearby. And the current is gradually increasing. So the current's getting stronger and stronger. Question 1. What direction does the straight wire's magnetic field point in the interior of the loop? Alright, I guess I have to do another right-hand rule here. I know that the magnetic field of the current comes from the field production rule. My thumb has to point in the direction of the current. So above the wire, my fingers come out of the screen. So I would put dots above the wire. And below the wire, my fingers go into the screen. So I would put X's below the wire. Let's draw those in. Dots above, the X's below. So the flux through the loop goes into the screen. Now I need to think about the induction. The current is increasing. The current's increasing, then the strength of the magnetic field is going to increase too. The more current you've got, the stronger the field is. So as the current gets stronger, I'm going to get more and more X's inside this loop. counteract that, I need to make dots. So the induced current has to have dots on the inside. We've already seen this arrangement a few times, but I'll do it again. To get dots on the inside, yeah, it's like a perfect fit. To get dots on the inside, if I am on the right, oh yeah, I need to drag myself over here. To get dots on the inside, I need my thumb to be going up on the right edge. Here are my finger dots. So that's a counterclockwise current. And last one. This is related to a device called a transformer, which we talked very briefly about when we were studying alternating current. Two wire loops are arranged, one above the other. A battery is then connected to the lower loop as shown. So these two loops are seen slightly like edge-on in perspective, kind of like looking slightly down on them. And I put a battery in the bottom one, so it's going to have a current flowing in it. The top loop does not have a battery. What direction is the lower loop's current? Well, you may or may not remember, but when you're looking at a circuit diagram, the long side of the battery is the positive, and current comes out of the positive. So the current is going clockwise. Oh, I shouldn't have revealed. No, I did want to make that. So the lower current from the battery, clockwise. And if I do a right-hand rule for that, I'm going to use the bottom. Now I'll stick with the right. So if I think about the right edge of the loop there, I know the current's going down. I don't know, I want to think of that as coming out of the screen. So here on the right edge of the loop, the current's like coming out of the screen towards you. Again, it's drawn in like perspective. So that means I need my thumb to be pointing out. And if I do that, then again, my fingers on that side, my fingers on that side of the wire are going down. So the magnetic field produced by this current, by the battery's current, goes down. Okay. What direction is the upper loop's induced current in the moment just after the battery was connected? So before the bottom loop is turned on, there's nothing there, right? If the battery is not here, there's no current, so there's no magnetic field anywhere. As soon as I connect the battery, this magnetic field comes into existence. So the flux through the upper loop has changed from having zero flux, because there was no field at all, to having a downward flux. So that means the change in flux is down, went from zero to down. My induced magnetic field then needs to point up to try to cancel out that change. I know that the induced magnetic field has to go this way. And since the magnetic field goes the opposite direction of the other one, the current also goes the opposite direction. You could go through all that with the right-hand rule if you felt like it, but it's pretty straightforward with this time. If I need an opposite magnetic field, that means I need an opposite direction for the current too. Then, lastly, what direction is the upper loop's induced current a few seconds later? Now remember, you only get induction when there's a change in the flux. So turning on the battery, that creates a change. But once the battery is on, then there's just going to be this constant current in the bottom loop. That means that the magnetic field produced by the bottom loop, that I've drawn in blue, that's also going to be constant. And so the flux through the upper loop is not changing anymore. So if you wait for the system to like warm up, the induced current will stop. In the moment that you turn it on, or in the moment that you turn it off, you're going to get an induced current in that upper loop. But in between, there's nothing. Now, in a transformer, as I mentioned, transformers only operate with alternating current. That was a big part of the whole Edison versus Tesla thing. With an alternating current, the current is turning on and off all the time. It's alternating. Sometimes it goes one way, sometimes it goes the other way. It turns off completely in between. So if there were an alternating current on the bottom loop instead of a battery, which makes a direct current, then the flux in the upper loop would be changing like all the time. And I would have a constant, I shouldn't say constant, I would have current, I would have induced current in the upper loop all the time also, because the flux is changing all the time. So that allows you to basically transmit an alternating current from one loop to another, strictly through this electromagnetic effect. You don't need a wire. And if you change how many coils there are, you can also adjust the voltage, which is how Tesla's system for alternating current was able to beat Edison's direct current system. Lets you switch the voltage around whatever you want. So again, with a direct current like a battery as in this diagram, you only get an effect in the moment that you turn it on or off. But if it were an alternating current source, then you'd have induction going on all the time. And some of the other videos that I'm going to link to talk about that same idea. And that is it. I don't think I've talked continuously this long in weeks, so I'm getting a little hoarse. Yep, that's it. Probably most of you found this confusing. That's totally fine. Everybody pretty much finds it confusing when it's new to you. You can watch my video as many times as you want to. You can watch other people's videos. You can read. You can come to my office hours. If you're confused, basically you have a lot of company. Don't worry about it. Okay, that's it.